Having done crystal lattices, different kind of crystal systems, now we know that lattice plus a basis becomes a crystal. We need to know the further properties of these crystals, and one of them is the vibration of the ions or the atoms from their mean positions, which are called as phonons. So, the quanta of lattice vibrations are called as phonons, and in that context we will talk about two simple models, namely monatomic and the diatomic lattices, and we will study acoustic and optical modes in them. Both the modes of course arise in diatomic lattice, and hence we will talk about more properties of the lattice, namely the specific heat of solids, basically the lattice contribution, and in that connection we will talk about Einstein and Debay's theory of specific heat. So, what is the simplest model of a solid? So, a simple model of a solid is just like you see a simple cubic structure with or maybe it is a face centered or rather a body centered cubic structure. There is one atom at the middle, and what you see are they are connected by springs. Okay. And these atoms kind of execute vibrations about the mean positions. The mean positions are shown as shown in the figure, and then they vibrate about the mean positions. This is because of temperature the vibration occurs, and we take this solid as if they are connected by these imaginary springs, and hence the type of force that they experience, or one atom or ion experience, is due to the presence of all other ions or atoms in this assembly, that is of the Hooke's law type, or we have these harmonic interaction between them. Okay. So, there is just a spring mass model. If you remember your classical mechanics, there is just a spring mass model of a solid, and given that this is simple enough and there are really no springs attached to the atoms or the ions, but this model works very well, at least in talking about a few properties such as lattice specific heat and so on. Of course, it has deficiencies that it cannot explain certain other things which arise because of the anharmonicity. So, we take a 1D crystal lattice. Of course, 1D is just an idealization, and just to make sure that we are really in a simple sort of regime, so that we can do calculations and so on. So, you see these atoms, each one of mass m. So, it is a monatomic lattice, just one kind of atom which are of mass m, and they are connected by springs, and the spring constant is written as gamma. I will use this spring constant as k for my calculations. Now, sometimes these k is misleading, because you also are going to have a wave vector that is denoted by k. So, the wave vector will be denoted by a small case or small letter k, and this is going to be denoted by a large k. Okay. So, we will denote it like a large k here. So, this gamma would be replaced by a large k, but other than that everything remains the same. A diatomic lattice, again in one dimension, has this structure that the effective unit cell becomes double, or you can think that there are two atoms, small m and capital M, such that the distance between the like atoms, that is the ones that is dashed ones, and the hatched ones, they are denoted by small m and capital M, and small m is not equal to capital M, but then you can also make that approximation that small m equal to capital M in your calculations and get all these modes, etc. So, the whole thing is that these are the atoms that are connected to each other by springs, and these springs will allow them to vibrate. Either they will vibrate in plane or they will vibrate out of plane, and we are going to talk about those vibrations and analyze this problem using this the equation of motion, which is written for a mass spring system. This is of course a coupled pendulum kind of equation that we are going to write. Okay. So, the simple application of Hooke's law, the Hooke's law says that the force is proportional to the the displacement and it takes place in the opposite direction, there is an elastic force. So, if you have a mass spring system, so this is like a a spring here and connected to a mass here, and this mass is given a small push in the positive direction or in the rightward direction, and then the spring gets stretched and the spring stores a potential energy, and this mass will eventually, because it's connected to the spring, it will come back to its position and it will go a little inside, that is, the spring will be compressed, and then this leftward and rightward motion will give rise to simple harmonic motion. And we have talked about classical harmonic oscillators and quantum harmonic oscillators. So, this classical oscillators of course have energy which is p square by 2 m plus half m omega square x square, and the quantum harmonic oscillators have energy which are n plus half h cross omega. So, let us deal with this problem classically and write down the equation of motion, and you know that equation of motion is often the starting point for classical analysis of motion. So, what we do is that we say that the force is proportional to x. This is called as Hooke's law. Let me write that. And if you have a force like that and force is given as minus dv dx in one dimension, or it is a minus gradient of x, that gives a v which is a potential energy, or we can write it as u. Let us just, because v would also be the velocity. So, let me change it to u. So, du dx, so u is equal to half k x square, where k is called as a force constant, and for given problem when the mass of the particle is m and it is undergoing an oscillatory motion with an angular frequency omega, then k or rather omega equal to root over k by m, that allows you to write this as half m omega square x square. So, that is a problem that is well known. So, what we do is that just going back to the picture that we have presented for a 1D solid, we write down the equation of motion. Now, there are two coupled masses, or rather the masses are coupled by these springs, and we have this, let us call this as a harmonic potential energy, which is half of k, and this is u n a minus u n plus 1 a. So, that is the kind of potential energy that we have, and that is so u is the displacement, u n a is the displacement of the particle, or which has a mass m at the nth location. Now, you see, if you look at this 1D solid, either of the pictures that you see on the screen, you see the ones that is the second one and the third one, they have neighbors on both the directions. And but the ones that are at the end, we have just drawn 4 atoms or 4 ions, but in principle a very large number of ions are atoms are they are connected by springs. Nevertheless, the ones that are inside or at the middle, excepting the end ones, they see the same environment, and but the last ones, or rather the end ones, they do not see the same environment, because the one is not the edge ones only see one neighbor. But there is a simple way to take care of this, is that we do a periodic boundary condition. So, we take this 1D chain and then connect it back to back, so that the the n plus 1th atom becomes the same as the first atom that you have. Okay. So, we will use periodic boundary condition, which is also known as the von Karman boundary condition. All right. So, this is the harmonic potential that we have. This is exactly what was written above. We have used a displacement to be x. Now, we have used a displacement which is given by the small u, and we have specified the nth location, or the nth atom or the nth ion, and that between n plus 1th ion. Okay. And of course, this is a square of that Okay. So, that is the form of the potential energy. Okay. So, we write down the force just by using this del u del x. So, this is equal to k, and then you have a u and n plus 1 a and minus u of n a. That is for the one side, that is n is connected to the n plus 1th term, plus there will be another term which is u n minus 1 a and a minus u of n a. So, we are focusing on the nth particle, the particle that is at the nth location. N is arbitrary, it can be anywhere in the lattice. So, it is connected to the n plus 1th site and the n minus 1th site, and this is what the force will look like. Okay. And if you write the force with this term, we are neglecting a negative sign here, or rather the negative sign is kind of absorbed in this inside this bracket, because you are focusing on the nth particle. So, if you write u n a on the left, then you have a minus sign. So, that is why it is reconciled. So, now let us write down these equation of motion, which is m u double dot n a. So, this is for the nth atom, which is del u harmonic del u. This is a small u and capital U. So, please make that distinction, and this is equal to n a, and this is equal to a minus k 2 u n a minus u n minus 1 a minus u n plus 1 a. Okay. So, there are these 2 u n a is the displacement, twice the displacement of the nth atom, and then minus the displacement of the n minus 1, which is lying on the left, and u n plus 1, which is lying on the right. Okay. And as we have said that we will use periodic boundary conditions, and periodic boundary conditions will allow us to write the u of n plus 1. So, there are capital N atoms in the chain. Okay. So, this is n is the number of atoms or ions, of course, in the chain. Each one is of mass m. That is the total number of atoms. So, u into n plus 1 a is nothing but u into a, that is the first atom, and you also have the displacement of the 0th atom is same as the displacement of the nth atom. So, these are the signatures of the periodic boundary condition, or the periodic boundary condition enters through these these conditions. Okay. So, in order to solve this equation, we can call this as equation 1, and then in order to solve it, we can assume a solution u of n a t, that is equal to proportional to exponential I k n a minus omega t. This is for all t, and the periodic boundary condition now requires that exponential I k n a is equal to 1. This is equal to exponential 2 pi n I, where n is an integer, small n is an integer, and capital N is what we have said earlier, that is the total number of atoms or the lattice sites that are involved. So, this is an integer. Okay. So, that gives the quantization of k. This is equal to 2 pi over a small n over capital N. Okay. So, you can also write it as 2 pi over L into n, where L is equal to, that is the total length of the chain, is equal to n into a, where a is the lattice constant, that is the distance between, or the difference between the coordinates of these two successive sites or particles or ions, atoms, etc. So, this tells you that if you change k by 2 pi over a, the displacement u n a, that is the displacement u of the nth atom, it remains unchanged. Also, this tells us that there are n distinct solution, one for each value of k, and for convenience you can put an index that goes with k that will make sure that there are these n solutions that are there, and these n solutions would be restricted between minus a to plus a. So, k this vector. So, now this make sure that you make a small k and a capital K. Capital K would go and was sitting at the the harmonic part. So, this k and then when we come to this wave vector that becomes a small k. So, that we can write it as small, I mean the k n as well, that will make it. So, k is or all these k n's are between this minus a to plus a. Okay, they are contained within that, and this is called as the first Brillouin zone. All right. So, if we substitute this ansatz in this equation of motion, we get minus. So, let us call this as equation 2. It can have an amplitude. So, this proportionality can be cut down, and one can write an amplitude, and putting 2 in 1, that is the equation of motion that you get, this equation 1. So, putting 2 in 1, what one gets is the following. So, it is a minus m omega square exponential I k n a minus omega t, and this is equal to minus k and 2 minus exponential minus I k a minus exponential I k a, and this is nothing but equal to minus 2 t 1 minus cosine k a and exponential. So, this Brillouin zone, let me write it here. So, this is the Brillouin zone, and so it is 2 k 1 minus cos k a. Once again, this is capital K, just to remind and sensitize you. If you use another notation, maybe gamma there. So, 2 k 1 minus cos k a and exponential I k n a minus omega t. Okay. So, here we are not using n as a subscript, but its n goes with a because we are talking about the nth atom. So, this is the equation of motion that it becomes, and one can really cancel this exponential I k n a minus omega t from both sides, because that is not equal to 0, that is a propagating wave. That gives us that omega, which is of course a function of k, the wave vector k, this is equal to a root over 2 k capital K and 1 minus small k a divided by m. Okay. And this is nothing but 2 capital K by m, and then there is a mod of sine k a by 2, and that is the behavior, or that is the dependence of this angular frequency of vibration omega as a function of k. Now, from a simple mass spring system where omega is a constant and just depends on the mass of the particle and the force constant, here of course there is a dependence on the wave vector, and these wave vector k, there are n in number, and these wave vectors are all contained in the first Brillouin zone, which is given by minus pi over a plus pi over a, where a is the lattice constant. Okay. One can see that omega is actually an even function of k, which means that omega of k is equal to omega of minus k. See the same problem, if you generalize it to more than one dimension, you would simply acquire a vector sign of k, where k becomes a more than one dimension. It is just a vector quantity, but all these simple calculations will go through. Okay. So, now this is important to note that there is for each distinct value of k, we get a unique frequency omega k. Okay. So, omega k actually yields 2 n independent solutions. 2 n means the capital N where n is the number of atoms in the whole chain. Okay. So, these solutions actually propagate through the chain, and there are two velocities that one can define, is called as a phase velocity, which is simply equal to omega by k, and we can also define a group velocity of these waves that propagate, that is wave packet propagates with this velocity, which is d omega by dk. Okay. Now, if you want to know that how the long wavelength modes propagate, now these are important because these long wavelength waves means that lambda goes to infinity, which means that k goes to 0, or when we say 0, we actually mean the small thing, because if you put k equal to 0, then you lose all information about that. So, omega becomes equal to root over capital K by m, and a, which is a lattice constant, and this small k, which is a vector. So, this is the definition, or rather this is the behavior of this angular frequency or frequency of oscillation as a function of this wave vector k. Okay. And these are known as sound modes, and these sound modes have of course this property that your Vp becomes equal to Vg, because your omega by k and d omega dk, they become same. And so, these have a relation. Why they are called sound modes is that they have a relation which is omega equal to Vs into k, and that kind of a relation is called as a sound mode. Of course, similar relation also the photons obey, which are quanta of the electromagnetic vibration, but there the speed is not the speed of sound, but the speed of light, which is given by c. Here of course, the Vs is the speed of sound, and we know this numerical value in say vacuum or in a metal, and so on and so forth. So, if we plot this, how would it look like? And that is an important thing that we want to usually see. So, this is your omega, and this is the k, and this actually the modes actually rises like this, and they nicely sort of saturate at the edges, and I have to draw it very symmetrically if I am not that precise, but you know that these are symmetric things. So, these are pi by a, and these are minus pi over a, and these are called as a sound mode. So, the close to k equal to 0, this region that you see here, let me highlight it, this region that you see here and here, these are the sound like modes, because these omega is linearly varying with k, which means the Vs or the sound velocity is a constant, which is given by this omega over k, which is nothing but this root over k by m into a, which all of these are constant for a given setup. So, this is what we learn from these monatomic lattice, and we get these modes which are called as the sound modes. As you go away from k equal to 0, of course, the non-linearities show up, and there are a few comments are in order. One is that if you go beyond nearest neighbor interaction, nothing much changes, because we have taken these while we wrote down this equation of motion, we have taken a nearest neighbor interaction, or the harmonic potential is between the two neighboring atoms or ions. But if you go beyond that and you understand that, or rather assume that there is a small contribution coming from the next to next near neighbor, or next to next neighbor, and so on, this problem only changes quantitatively, rather the qualitative, there is no qualitative change that one notices here. And you will have more terms there, because then you have n minus 2 and n plus 2 atoms involved, and n minus 3 and n plus 3 involved. So, you will have a complicated equation, but you can still consider a solution to be similar to what we have taken it here as equation 2, and we can do this problem exactly similarly. So, there is no qualitative change that occurs, there will be change in numbers of course. Now, there is another important thing. So, this is nothing or no qualitative change in the spectrum. Now, what happens when you go to k values beyond that, and I am just drawing it here, where say this is from minus a pi by a to. So, this is your say minus pi over a, and this is pi over a, and this is say I should draw it a little bit in scale at least. So, so this is 2 pi over a, and so on. Okay, so, this is the 0 that is there. So, we have these modes that will rise like this, okay. And then as you increase k, it will go like this, okay. And there is always a reciprocal lattice vector that can be subtracted from the the extended Brillouin zone, which goes beyond the first Brillouin zone, which is between minus pi by a to plus pi by a. It always comes back to some point in the first Brillouin zone. What I mean is that if you take a point here, let me show it by a color. So, and subtract a reciprocal lattice vector, it will come back to the point inside the Brillouin zone, and this tells you that the description that we gather from the first Brillouin zone is good enough. Okay. And there is another thing that is there. So, this is about the extended zone scheme. I just did it here. So, extended zone, as you go beyond the first Brillouin zone, the description is always contained within the first Brillouin zone. And if you think that you would try to calculate the group velocity, say for example, using the full expression, then the full expression has this velocity expression, group velocity expression is equal to a cos k a by 2, and so on. So, this group velocity is important for us, because this group velocity tells you that the V g equal to 0 at k is equal to plus minus pi over a. So, if you put k equal to plus minus pi over a, you get cos pi by 2, which is equal to 0, and that tells you what I was saying here. Let me again put a highlighter here and maybe use a different color. So, here the velocity, the group velocity goes to 0, and that is why it just kind of flattens. So, this spectrum flattens there, and there is no group velocity at the edge of the Brillouin zone, which can be seen from here. And the final remark that one can make here is that one can actually calculate these force constants from these equation, which if we just simply square it up. So, omega is a function of k. So, we can write a k here, and we can continue writing k's. We have written omega as a function of k, or we can write omega with a k in the subscript. Either way is fine, but let us follow one convention, which is omega k. So, we can do a omega k, and this is equal to 2 over m capital K over 1 minus cos k a. And what you can do is that you can calculate or rather extract this capital K, which is a force constant, by multiplying it by some cos k prime a, and then integrate it over the Brillouin zone, and that would sort of extract out this k there, because this cos k a and cos k prime a will have an orthogonal relation between them, and then one can do that. So, I just write down this step and say that multiply by cos k prime a and integrate over the Brillouin zone, the first Brillouin zone. So, we write Brillouin zone by Bz, and so that should be fine. So, let us now go to the diatomic lattice, and that diatomic lattice is a little more complicated because of the presence of two ions, and let me show you the equation of motion, and the solution exactly proceeds in the same manner as we have seen for the monatomic lattice. So, this diatomic lattice going back once again. So, there are two atoms, each one has mass m and the other has mass capital M. So, small m and capital M, each of them is a small m has a neighbor as a capital M, and capital M has a neighbor, or rather two neighbors as small m, and same goes for the small m, it has two neighbors as a capital M. And the distance between the m and capital M is called as lattice constant, which is a, and because they are alternatingly placed. So, the distance between two small m's or two capital M's is equal to 2a. So, the unit cell actually becomes twice as big as that in a monatomic lattice, because the unit cell will have to contain the entire structure, which this is exactly what we have said in the last class, the structure that can be replicated to get the entire lattice. So, let me use a color here. So, the unit cell is actually now this, which is basically the boxed one, it is already boxed there. So, that is the unit cell, and then you have it at 2a. Okay. So, we have these alternating atoms which are of small mass, small m and capital M, and we can write down the equation of motion for okay, let me use this black color that we have been using. So, we have for small m, we have these m d2 u 2s. Now, we will just use this notation because we have these the unit cell has doubled, and this is equal to k and u 2s plus 1 plus u 2s minus 1 and minus u 2s. That is a similar equation that we have written down. So, let us call this as equation 1, and for capital M we write down a similar equation. So, m d2 u 2s plus 1. So, this is in the s unit cell. So, this dt2, this is equal to k, and we have this u 2s plus 2 plus u 2s and minus 2 u 2s plus 1, and that is the equation of motion. And then one can assume solutions of the form which is exponential I or say a exponential I k into 2 s a minus omega t. Ultimately, we want these omega as a function of k, and u 2 s plus 1. So, this is for mass small m, and this is for capital M, and this is a b exponential I k 2 s plus 1. Well, let me write it with a square bracket then. So, this 2 s plus 1 a minus omega t. So, we have not done anything else excepting that these are two different atoms, and their amplitudes of vibrations would be different, and we have assumed similar solutions, but with different amplitudes and so on. So, in general, one has a k to be also different, but we are assuming the k to be same in this particular case. So, what we do is that if we take these as equation 3 and equation 4. So, in principle we have these, as I said, k1 and k2 to be different, that is two different k's and two different omegas. However, we take them to be same here and will not cause any trouble in the analysis that we want to make. So, what we do is that, so we get a 2s minus 1. So, this is from 4. So, so this is from 4, we get u 2s minus 1, or let me write it for 2s plus 2. So, this is from 3. So, 2s plus 2 is equal to exponential 2I k a u 2s. Remember, 2s plus 2 and 2s they correspond to the same atom, that is each one with small m. Okay. And similarly from 4 we get u 2s minus 1, this is equal to exponential minus 2I Ka u 2s plus 1. Okay. So, this is say equation 5 and 6. Okay. So, 5 and 6. So, these are the same equations, and then if you put these solutions 3 and 4 and using 5 and 6 and so on, we get these equations which are minus m omega square u 2s, this is equal to capital K, this is 2s plus 1 plus exponential minus 2I Ka u 2s plus 1 minus 2 u 2s, and that is one equation, and we can call it as or both the equations can be called as let me just rearrange this equation. So, this is equal to minus m omega square plus twice of k u 2s, this is equal to k, and 1 plus exponential minus 2I Ka and u 2s plus 1. So, this is the coupled equation, let us call it as equation 7, or we can, what we can do is that we can combine these two combined can be called as 5, these two equations, that is this equation and this equation can be combined called as 5, and this let us then call this equation as equation 6. Okay. So, that is connecting the displacement of mass small m to that of capital M. Okay. And so, if we put them into equation number 2, then what we get is that minus capital M omega square plus 2 k, this is equal to okay. So, this is, and so 2 u 2s plus 1 and k 1 plus exponential 2I Ka. Please do these steps yourself so that you are comfortable with this. So, we have written down an equation of motion in 1 and 2 for the masses small m and capital M, and have taken these solutions very similar to the ones that we have taken earlier, and put them into these equations. So, these are propagating wave solutions, because these are wave equations, and then the solutions will be some waves. So, these propagating waves are put there, and omega has to be calculated from that. So, this is say equation 7, and from 6 one gets u of 2s plus 1 divided by u of 2s. This is the ratio of these the displacements of the two masses, and that is equal to small m omega square plus 2 k, and this is divided by k into 1 plus exponential minus 2 I Ka. So, once again make this distinction that small k is the force constant and large k is the force constant and small k is the wave vector. So, this is from 6, and from 7 we get a similar equation, which is u 2s plus 1 divided by u 2s. This is equal to k and 1 plus exponential 2 I Ka divided by minus m omega square plus 2 k. So, these are equation, this is equation 8, that is equation 7, and so let us call this as these two as maybe equation 8, and so maybe 8 and 9, that will be more appropriate. So, these are same ratios, and if we equate these 8 and 9, which is the most natural thing to do here. So, if you do that, then what you get is that minus small m omega square plus 2 k this is equal to k into 1 plus exponential minus 2 I k a. This is equal to k 1 plus exponential 2 I k a divided by minus m 2, I mean this capital M omega square plus 2 k. And that gives you this solution for this omega. You can now solve omega in terms of, so solve omega in terms of capital K, small m, capital M, and of course the wave vector k, so that you get omega as a function of k. And once you do that, what happens is the following. So, we have these omega square, which is equal to capital K 1 over m plus 1 over small m and capital M, and then there are these plus minus signs which are coming from here. These are like 1 over m plus 1 over m whole square minus 4 m1 mm small m capital M and sine square k a by 2. So, this is actually one can get a omega here, and these if you put a square root of that, you get a omega here, and there are two of these masses. And if you define alpha to be the the ratio of the two masses, that is small m by capital M, and then what one gets is this nice modes that are there, and we have to again restrict ourselves between minus pi over a to plus pi over a, and we have these acoustic modes that you see here. Okay. They are very symmetric. If it does not look like, please draw it. It is a little hard to draw on the left side. Okay. That looks more or less straightforward, and so this is so one can actually do it for a number of things. So, these are called the acoustic modes that we have seen, and now because of the plus minus sign we will get the optical modes, other modes as well, and these other modes will kind of give that. So, there are modes like this, okay, and you can tune alpha and can get different modes such that these gaps kind of merge as a function of alpha. So, we have drawn it for one. So, this is omega as a function of k, and we have just drawn. So, these are called as the optical modes, and these are called as the acoustic modes, which is what we have. The word acoustic means sound, I mean related to sound. So, acoustic modes and optical modes. So, these optical modes are higher, and you can tune them, you can plot them and show that for alpha equal to 1, which means that the two masses are same, you have a merging of that. I will just draw it using a color and then probably remove it. So, this is the, or we can keep it as also. So, this is like a sort of plot for, so this is for alpha equal to 1. There is no gap between the optical and the acoustic modes at the Brillouin zone. Okay. So, the sound velocity would be given by here. So, the sound velocity, which is Vs, which is equal to omega over k, which would be given as a over 2 and root over capital K divided by twice of small m plus capital M, and that is the velocity of sound for this particular cases. Okay. So, let us just sort of see that what we have learned so far, and we have actually talked about phonons, and so these are a set of moving quasiparticles with momentum p, which is the momentum is h cross k and the energy is h cross omega, and we have this h cross as a Planck's constant, and this is maybe considered in correspondence with each of the travelling plane waves with wave vector k and frequency omega. And these quasi particles these are quasi particles, that is a technical term, it just means dressed particles. These are quanta of the lattice vibration. We have used this word before because these in analogy with photons, which are quanta of the electromagnetic fields, and these are the lattice vibrations have important implications on the crystal properties. So, higher the temperature of the crystal, this more intensely, or these atoms will oscillate about their equilibrium position with larger amplitudes, and when the amplitude of the vibration exceeds certain critical value, melting begins and the crystal structure would be entirely destroyed. But however, the harmonic theory that we have learned so far will be unable to take into account this melting, or this the melting of the, because in this situation, in the harmonic approximation, the expectation value of this u, or the mean displacement, always goes to 0. So, that will never diverge even as a function of temperature. So, this is unable to, this harmonic theory is unable to take care of the melting of solids. Okay, and we will see in just a while that the lattice heat capacity is a quantitative characteristic of a crystal's ability to store heat in the form of potential energy, and the heat capacity per atom is found to be approximately equal to 3 K. This is not K B, but this is K B. The K B is a Boltzmann constant, or high temperature. So, this at high temperature it is 3 K or 3 R, as we say, for if you multiply K by N, N is the number of atoms, or is proportional to T cube as T approaches 0. So, we point out again the deficiency of the theory of crystal vibrations and harmonicity, that is not included there, and in reality the linear forces are not strictly proportional to the displacement, but they are anharmonic effects that need to be taken into account. And this non-linearity of the interatomic forces are often small because the amplitudes of oscillations are small. However, by virtue of this non-linearity, individual normal vibrations are not independent, but they are often interconnected, and the resonance is possible, as it happens in a system of coupled oscillators or coupled pendulums. The anharmonicity explains the thermal expansion of the crystals and hence melting, and this would register severe deviations from the these Dulong and Petit's law for specific heat and in the high temperature regime. And diamond is one such example where you see a lot of deviation from the Dulong and Petit law even at large temperature. So, how do we experimentally determine lattice vibrations? There are various experimental methods for determining the lattice vibrations. Excitations by means of infrared radiation is one method of studying lattice vibration, and it is possible not only detection of this vibration, but also determination of this frequency by the infrared radiation. And then there are studies of inelastic scattering of neutrons in crystals. It makes it possible to determination of the dispersion law and the polarization of normal vibrations. The dispersion law can also be constructed using the diffusion scattering of the X-rays. These are some technical experimental facts. We are just stating the facts. And also this Mossbauer effect that makes it possible direct determination of the mean squared displacement and the moment of the atoms in the lattice vibration. So, we come to the specific heat of solids, which is one of the last things one describes for the lattice contribution, and the electronic contribution comes separately. And in this connection there are two theories. One is called as the Einstein's theory, and the other is called as a device theory. And the Einstein theory was that or Einstein's law or Einstein's specific heat. It says that all the atoms, they vibrate with one single frequency. That's like too much of an approximation, but that's what he thought it to be correct. It's like a delta function, there's just one frequency involved, and all the atoms or the ions, they vibrate with that frequency of oscillation. And we know that the energy is given by for such oscillators in the quantum limit as n plus half h cross omega. Omega is nothing but root over k by m, and n can take values which are 0, 1, 2 and so on. So, there is a 0 point energy that's involved here. Now, one can take a statistical route in order to calculate this specific heat. So, what one can do is that one can write down the partition function, which is exponential minus beta En and sum over n, and from there you calculate the average energy. So, the average energy is nothing but equal to minus 1 by z del beta. We have written z. Taking a del z del beta is not difficult, and in fact, this has simpler expression which is del beta of log z. So, you can actually calculate z in a closed form by doing this sum, and n goes from 0 to infinity. It becomes a GP series, or rather we can write it down exponential half beta h cross omega, and then there is a sum over n equal to infinity to 0 to infinity exponential minus n beta h cross omega, and this GP series can be summed up. One gets a minus half beta h cross omega, and this is 1 minus exponential minus beta h cross omega and so on. So, one can take a log of z and then calculate this average energy. So, this is average energy. And why do we need the average energy? Because the specific heat is just del E bar del T. So, we can calculate this, and just a little bit of algebra will get it. So, there is a half h cross omega minus h cross omega exponential minus beta h cross omega divided by 1 minus exponential beta h cross omega. And what you do is that you take a derivative with respect to t, and if you do not do that, you can also do a del E del beta del t. So, that is also going to give us so del E del t is this, and this is nothing but minus 1 over k t squared, because beta is 1 over k t. So, what one gets is that for t to be high, for t large, that is when beta h cross omega, which is nothing but equal to h cross omega over k t, that is much smaller than 1, because k t is much larger than h cross omega. You can do a exponential x to be equal to 1 plus x and so on. You can cut down all other terms. So, these exponentials that you see on the step above can be expanded, and one gets the average energy equal to h cross omega divided half plus 1 by beta h cross omega. That is your expression, and this is nothing but equal to h cross omega and divided by beta h cross omega. You can neglect this half because the temperature is large. So, beta is 1 over t. So, the t goes in the numerator of the second term. So, t is large. So, you neglect half. So, it is h cross omega by beta h cross omega. So, this is equal to it's equal to k t. So, del E del k, that becomes equal to k, which is the result that you get. So, for 3n oscillators, 3 is the dimension and n is the number of oscillators in each dimension. For 3n oscillators, we get a real, so this del E del t, which is nothing but equal to CV specific heat, this is equal to 3n k, which is equal to 3 r, and this is called as a Dulong and Petit law. So, we recover the Dulong and Petit's law correctly even with a crude approximation, that is all the atoms are vibrating with the same angular frequency about the mean position. However, the low temperature behavior, which is another important thing that one needs to worry about. So, at low temperature, so in the other limit when h cross omega is greater than t, one gets a CV equal to a del u del t or rather del E del t, and this is equal to del E del beta del t, as we have said, and this with a little bit of calculation one actually gets it as 3R, and this theta E it is called as an Einstein temperature. We will just define it in a while. So, exponential theta E divided by T, exponential theta E divided by T minus 1 whole square, where theta E by T is equal to this ratio, which is h cross omega by kT. So, this theta is called as a characteristic temperature or the Einstein temperature. Now, of course, in the other limit, that is T much. So, this is the general expression from what we have found out. We are still not at low temperature. So, let me remove this. We will be there at low temperature. So, at any temperature rather. Okay. So, T greater than theta E, which is h cross omega by k, you have CV coming out as equal to 3R, but in the other limit, so this is fine. So, this is the Dulong and Petit law, that is I am sorry, Dulong and Petit dP, that is obeyed. In the other limit, which is T to be much smaller than this Einstein temperature, your CV comes out to be 3R theta E by T whole square and exponential minus theta E by T. Now, this is a slightly complicated dependence, and it goes as 1 over T square and exponential minus 1 over T. And this is much smaller than what is observed experimentally. So, this is much smaller than experimental values, which means that this is incorrect even though the or experimental values. So, this tells you that this oversimplified picture of all the atoms vibrating with the same frequency may not be correct, and what Debye did was to come and correct it, and he said that not all the atoms vibrate with the same frequency, but there is a distribution of frequencies, and with a cutoff which one calls a Debye cutoff, because Debye actually proposed it. So, Debye's theory or Debye's law says that there is a cutoff, and this cutoff actually has I mean, according to his theory, it has a smooth cutoff, but in real materials when people have actually calculated the density of states, it shows kind of rugged structure, but nevertheless these picture is correct that not all the atoms vibrate with the same frequency, but they have a distribution of frequencies, and this distribution gets cut off, that is, its distribution ceases to exist beyond omega equal to omega d, called as a Debye frequency. And in that one can actually find out that how to calculate these Debye or rather the density of states. So, the density of states in 3D, which has been shown in different parts of the course. So, we have a GK dk, this is equal to V, which is the volume, by 8 pi cube, and then we have a 4 pi omega square and a Vs square, and a d omega by Vs, and we are assuming a dispersion which is omega equal to Vsk. So, I will sort of leave it to you to figure out, and it has been done at other places. So, it is omega square is the dependence and then V s cube d omega. So, this is like a g omega d omega. So, how many modes are there between omega and omega plus d omega? That is phonon modes or the lattice vibration modes, that is given by this variation, which is omega square variation, and this is exactly what we have said, that these variation really looks like this. So, for a Debye solid, this is like the variation with a cutoff. So, this is your g omega versus omega with a cutoff at omega d, whereas in real systems you have you see there is some kind of a sort of this real crystals, which is very rugged. I am just saying it is a schematic plot and it is not drawn to scale, but it is like this, whereas there is a omega squared dependence that you see there. Okay. So, in this oversimplified or rather this is relaxed, not as simplified as the Einstein case, but with this distribution of frequencies, what one get is that we get a correct result, and let us see how that comes. So, what can be done is that one can find out that this omega d by equating the number of modes, which is 0 to omega d g omega d omega. So, that is the number of phonon modes. You integrate over all frequencies from 0 to omega d, and that gives you omega d cube. This is equal to 6 pi square V s cube n by the volume V. So, that is the cube root of this will give you the Debye frequency. So, that is the cutoff frequency for our case. Okay. And now, we can write this down as the Debye wave vector. Now, this has to be written as a small k. So, that k d is equal to omega d by V s, that is the dispersion that we use. This is equal to 6 pi square n over V, and then we have a 1/3 here. So, you can calculate the average energy now by integrating this d omega g omega and of course, the average energy and now the Bose distribution function. So, because these are phonons are they obey Bose-Einstein statistics. So, this is the general scheme, that the average energy is equal to the quantum of energy g omega, then you have f, either Bose or Fermi, here of course is Bose, and this integral from over all possible frequencies. In this particular case, it should in principle go from 0 to infinity. In this particular case, it goes from 0 to omega d, and that will give you the average energy. Once you get the average energy, you can take a derivative with respect to temperature, which should give you the specific heat. Okay. So, if you write all of that down, so it becomes equal to 3 V h cross 2 pi square V s cube 0 to omega d, and omega cube d omega, this is what you saw, the omega square was the density of states, and then there is another omega, all the constant terms have been taken out, it is h cross omega by k t minus 1, and if you take this quantity x to be equal to h cross omega by k t, and take this x d to be equal to h cross omega d by k t, then of course, so this is let us call it as a Debye temperature in analogy with the Einstein temperature. So, this Debye temperature actually comes out to be h cross V s divided by k and a 6 pi square n over V whole to the power 1/3, and these the average energy comes out to be equal to 9 k t t over theta d whole cube 0 to x d. We have defined x d. So, it is x cube divided by exponential x minus 1, and this particular thing which is has a value which is pi to the power 4 by 15. So, your CV becomes equal to a del E del t, and we lose this t in the process of differentiation. So, it becomes 9 n k t over theta d, and then this integral is going to give us pi 4 by 15. So, this again at large temperature T to be much greater than H cross omega, or KT is much greater than H cross omega, we recover CV equal to 3 R. At low temperature, that is, the low temperature means that your KT is smaller than H cross omega, and your CV becomes equal to 3 n k T over theta d whole cube, and we have pi, so there is a 9 there, and then there is a pi 4 over 15. You can do some simplification by by this 3 and a 5 and so on. And nevertheless, what is important here is that CV is proportional to T cube, and at low temperature this is there is a all the solids actually show this T cube behavior, and that is why this is so very important, and it sort of removes the inconsistency with the experimental data, and one gets this at low temperature CV goes as T cube. In fact, there is a simple way of seeing this, because so only the lattice modes, so a simple picture, okay, without doing all these extensive calculation. So, the lattice modes within with energy which are H cross omega less than equal to KT, or of that order of KT will be excited. Okay. And how many such modes are there? That is obtained by this number of modes, or number of modes. They are proportional to the density of states, which are like omega by omega d whole cube. Okay. And so, this is really like the thermal wavelength divided by the Debye wavelength. So, this is the KT by KD whole cube, and KT, so the thermal wavelength. So, this KT is the thermal wavelength, and KD is the Debye wavelength, or rather a wave vector, thermal wave vector. And the thermal wave vector can be defined as like H cross Vs into KT is same as T. So, the number of modes that you get, they go as a function of temperature, they go as T cube, and so there are so if you really think that more careful ones will give you a T over theta d whole cube. So, and each one will have energy 3 kT. So, each mode kT, and so 3 you multiply this. So, there will be the temperature dependence for the average energy is T to the power 4. I am just neglecting all other factors. So, C actually goes as T cube, which is what we have said. So, it is just a simple picture and doing back of the envelope calculations, that you calculate the number of modes that are excited at a temperature T, and then each one of them has an energy which is KT, or 3n KT for the full 3n modes. Multiply them, that will give you the average energy, take a derivative with respect to temperature, that will give you the specific heat. So, we get this T cube law, which fits very well with experimental observations. So, we shall stop here, and we have done this crystal part and the lattice vibration completely here. Thank you.